This video is about multi-user programs. These are programs that talk to more than one user at the same time. It's easy to imagine a variety of such programs. For example, a multi-user debugger that allows multiple users to debug a program they've developed together. In fact, any program that solves a non-trivial problem is inherently a multi-user program because it can let people collectively solve the problem. At Purdue, we are investigating issues in designing, implementing, and using these programs. The question we will try to answer in this video is, what should be the coupling between the users of a multi-user program? That is, which of the actions performed by one user should be shared with other users, and when should they be shared with them? This question is of interest to the users of a multi-user program, who would like to know how others are coupled with them, to the implementers of the program, who would like to know what coupling to define for the program, and most importantly, to the designers of a framework for generating multi-user programs, who would like to know what kind of coupling they should support. We are currently building such a framework called Suite, and therefore are very interested in the coupling question. We will provide a preliminary answer to this question by illustrating the coupling model currently supported by Suite. What you see here is an example of a Suite multi-user program. The program manages the budget of a group of users. It shows the list of current budget items and the total amounts available, allocated, and spent. It also provides a template for adding a new item. It is currently interacting with three users, user A, B, and C. For this video, I have created all user interfaces on one screen and will be playing the roles of all three users. So let me begin by playing the role of A. Let me change the view of the rent item by aligning it. Let me change the color of the template. And now let me change the value of the template. Notice that nothing interesting happened. A's actions were not seen by others. Let us make this session more exciting by committing A's local changes. Notice the flurry of activity that just occurred. A's change to the allocated field was sent to both B and C. Also, the change was sent to the program, which inserted the template into the list of current items and updated the total available and allocated fields for all users. However, notice that A's view and format changes were not sent to B and C. We can now state the Suite coupling model. Semantic changes are sent to other users at the same time as they are sent to the program. Syntactic changes, such as view changes, are never sent. We believe this is typically the most comfortable coupling among users, more comfortable, for instance, than the popular WYSIWYG or what you see is what I see coupling. This is only the default coupling supported by Suite, and there is a variety of circumstances under which it does not work so well. Consider this situation where C changes the template to add a new item, and B also edits the template to add his own item. This is perfectly desirable interaction since it allows the two users to work concurrently. In this situation, however, the users do not want to share the values of their templates. Therefore, Suite provides a coupling window, which is just displayed on the screen, and which can be used to change the default coupling. Here, C uses this window to unset the value coupling for the template. Now when he commits his template, his value does not override A's and B's copy of it because it is no longer coupled with them. The value coupling attribute is defined for each displayed data structure. So it is defined for both the name and allocated fields of this record. Suite allows the field to inherit an attribute from its parent record. That is the reason why C was able to disable the coupling for both fields by defining the coupling attribute once for the whole template. The coupling was not removed for the other data structures. So if C changes the spent field of this item and commits it, this value is communicated to all users. Let us make the template public once again. Now let us change the value of this template in B's window. And this time, instead of executing the commit command, let us execute the transmit command. Like the commit command, this command sends the value of the template to other users. But unlike the commit command, it does not send it to the program. As a result, the users can collaborate on this value before they commit it to the program, and then any one of them can commit it. Now C makes the collaboration even closer by changing the transmit event field to increment. We now have the highly synchronous mode of collaboration, as C types A and B see his input incrementally. However, if A types, the other users do not see his incremental input. That is because A has his own set of coupling parameters and has not requested incremental transmission. Let us display his coupling window and change his transmission event to increment also. Now his input is also sent incrementally. Notice two things on the display. First, user A made an error by allocating more than what was available. Second, A's semantically incorrect input was sent to all users. That may be desirable, since C can now help him cut down on his proposed expenses. These two sliders represent two dimensions of synchronization. The transmit event slider allows the user to send a value incrementally when the value is completed, periodically with a specified period, at a particular time specified by the user, or when the transmit command is explicitly executed. The transmit correctness slider allows the user to send raw, passed, validated, or committed values. The listen sliders here allow a user to control which of the values transmitted to him are actually received. Let us change A's listen correctness slider to validated. Now, if C enters an erroneous value, it is sent to B but not to A, who is not listening for erroneous input. In general, each user independently indicates his coupling preferences, and the system does an automatic matching at runtime of these preferences. These buttons let users share various properties of a data structure. We saw value sharing before. It lets users share values of data structures. We can also share formats. If A now changes the color of the template, the color is changed in all windows, and so we get uniformity if we want it. We can also share views. So if user A elides this item, it is elided in all windows. We can further increase the collaboration by sharing selections, scroll bars, mouse positions, and so on until we finally get visibus coupling. Few computing concepts are complete without recursion. So let me show you how we can recurse on coupling. Suite supports a coupling attribute, which determines if these coupling attributes are themselves shared. By default, they are shared. So when A adds access coupling, the access coupling is added to the other windows also. If one of the users wants to diverge from the common coupling scheme, he has to simply disable coupling. If two users diverge on the coupling they want, then the system takes a conservative approach. It chooses the lesser sharing. So if A wants view coupling but C does not, then the views are not shared. So we have seen how users can precisely choose the coupling degree they want. This is crucial because if the degree is too low, they may not be able to collaborate the way they want to. And if it's too high, they may find the coupling bothersome and inefficient and therefore not want to collaborate. Now, if you're worried that as an end user you have to learn and set too many parameters, let me lay to rest your fears. Typically, the default coupling scheme will work just fine for you. If it does not for some application, it's quite likely that the underlying program would have defined the coupling attributes you want. If that also does not work, you can always get coupling attributes from some other enterprising user who is willing to redefine the program settings. If that also does not satisfy you, well, aren't you glad you have control? And you can always learn this model incrementally. Okay, so what are the new principles we've seen here? By default, only semantic objects should be shared. Users should be given the choice of also sharing user interface objects such as views and formats. They should be able to synchronize based on both events and correctness levels. Each data structure should be associated with its own coupling attributes. Each user should be able to independently set these attributes. Coupling attributes should be inherited and themselves coupled. If two users disagree on the coupling they want between them, take the conservative approach. This is not completed work, and we are currently working on flexible audio coupling, policies for setting coupling parameters, user-defined coupling parameters, and the influence of coupling on concurrency control, undo, redo, and access control.